Hello everyone, my name is Jurgen Vanhamel and I'm the representative for Belgium. I would like to first give you a little bit of an overview of who I am, a little bit about my experience, and then I will talk a little bit about my research in which I'm involved in. I'm a Belgian citizen, I still live in Belgium, I'm 36 years old, and I'm currently an assistant professor at the TU Delft in the Netherlands, at the Faculty of Aerospace Engineering. But besides that, I'm also linked to KU Leuven. I'm also an assignment there, and hence that's why I am the Belgian representative. I'm a visiting professor in Leuven where I teach courses related to telecommunication. And besides that, I'm also the coach of a student-based project which is called ITER, in which they are designing a re-entry CubeSat. I will talk about that later on during my research slides. A little bit of list of experience before I became an assistant professor at TU Delft. And in Leuven, I was a civil professor at Belgian Defense, where I taught courses related to electronics, antenna design, radar, and so on. And then I changed my career towards the Royal Belgian Institute for Space Aeronomy in Brussels, which is a federal research institute. And there I worked on different ESA missions like Picasso, where I designed together with other colleagues a sweeping Langmuir probe. And then I was, let's say, assigned as a system engineer for the Altius mission, which is also an ESA mission, Earth observation mission, which will be launched soon. And at the end, I became a program manager for Envision, specifically for the instrument events package. As a side effect, that's how I call it, there are also other instruments based on the space-based design, like for instance an NO2 camera and an ASPA instrument, which is used for observation of the auroral light. We will talk about that later on. So besides my professorship at TU Delft and KU Leuven, I'm also involved in guest lecture at the Technical University of Berlin. And as a side note, I collaborated in 3 space contacts via the so-called ARIS program. It's a radio amateur program where students can talk to astronauts on board the ISS. Let's dive a little bit into the research field I'm in. So my core is, let's say, using RF in 2 fields. One of them is using RF radio frequency steering for acousto-optical devices. An acousto-optical device is what you see in the middle of the slide. It's a small passive device. It can be used as a filter where you can select different optical wavelengths. And it can also be used as a deflector, as you see on the bottom, or even as a modulator to modulate a signal. So there are different possibilities. You can use it in space applications, but also on ground-based instruments. They have a nice application field. And if you look into the applications where these devices can be used, we talk about remote sensing, ground-based, but also space-based. That's a key element. It can be imaging, but it can also be scanning. And there are different possibilities with these devices. Now, looking into the acousto-optical device, I won't go into too much detail, but just to show a little bit what it is, it consists of a crystal material. It's some kind of transparent material. Depending on the optical wavelength, it's a different material. And light which enters on the left is split in 2 beams. One beam is a diffracted light beam, is the one that you want, and the other one will be blocked. And you can select these different optical wavelengths by applying an RF signal. And this RF signal is applied to a so-called transducer, which converts the RF into sound waves. That's why we talk about acousto-optical devices. And the conversion is done by a transducer. So by changing the frequency and the power level, you can actually select different optical wavelengths. That's the idea behind this system. Now, if you implement this in an instrument, it looks a little bit like this. So light comes in, you have optics, then you have your filter device, and then you have some optics, some back-end optics, when at the end you can image the observed scenery actually via a camera system. So my focus is around this acousto-optical device, and in this case it's a tunable filter and the driving system in order to select different optical wavelengths. Now let's zoom a little bit in. So for driving the system, you need a generator and an amplifier, and then of course you have to miniaturize this because it's quite bulky, as you see on the bottom. But to make it space qualified, there are only a limited amount of components that you can use if you want to use it, for instance, in an ESA mission. So you have to have a very flexible design, and you have to miniaturize this on volume and mass, of course. And that's one thing of the research. And the other thing is, of course, purely focusing on these AOTF, these acousto-optical devices, because there is a matching network, there is a transducer, there is material. So this is more fundamental research in which I try to investigate what kind of material can be used as an acousto-optical device and how can we actually adapt this impedance matching network, because you have to match the RF impedance or the electrical impedance to the acoustical impedance. So those things is actually the focus of my research, looking from an RF point of view. Some applications, as said, an NO2 instrument is what I designed in my previous job at VISA. So together with the colleagues there, we designed this functional instrument. On the left side, you see there is electronics. Now the idea is to further miniaturize this electronics in order to fit it inside a CubeSat. That's the work I'm currently doing. And by building this instrument, we could test it already in different applications or in different environments. This is a picture taken at the Etna volcano where we try to see if NO2 comes out of the volcano. And then there is the horizon of Brussels, which is the bottom picture. So as you can see, I'm sorry, in the middle you see the horizon of Brussels, and on the right side you see the slant column density of NO2. And there is a one-to-one translation between what you visibly see and what the slant column density is on the right side. And in that way, you can actually determine the concentration of NO2. Another application is this ASPA instrument, is to detect the polarization of auroral light. So it's a bulky instrument. It had to be quite bulky because there were heaters inside and so on. So we're currently thinking of further improving this instrument together with VISA. And other applications are, for instance, solar spectral irradiance instrument design or an SO2 instrument. There are different approaches. By changing the application of the RF signal, for instance, it can be pulse-based, you can actually do different kind of things. That's the idea. Now going to KU Leuven, there is the coaching of this ITER project where they are designing a re-entry CubeSat. So they already analyzed the heat shield, which kind of material can be used, what would be the size, and so on and so on. And on that project, I think about implementing a fiber brack grating structure in order to do a health monitoring system. With health, I mean that I measure the stress, strain, and temperature of the heat shield in order to see what happens with this heat shield during re-entry. And also on that field, it's optics. It's not purely RF, but it's optics. It's one of the projects on which I'm working currently here at KU Leuven. A side effect, let's say another application field for RF signals, because RF is, let's say, the main thing of my research, is using this to monitor space weather. This setup you see here on this slide is to check what is the polarization shift which occurs with a radio signal once it is reflected against the ionosphere. And that actually, this atmospheric behavior and these variations of this ionosphere is also part of my research. And currently I'm building a so-called RAPSI instrument. It's a radio amateur beacon system which will fly hopefully on board the new developed Delphi PQ satellite here in Delft. It's a very small satellite. It's only 15 by 5 by 5 centimeters. And we will to monitor in the 6 meter and 10 meter band, which means we need quite extended antennas. And there are a few students in Leuven working on the design of this antenna system. So there is still a lot of work to do. But again, this is also to monitor specific behavior like sporadic E. That's something I'm also involved in. There are some future ideas. The acousto-optical devices, of course, can be used in different setups, like laser-sat communication is also another application where it can be used, but also miniaturization, of course, of the acousto-optical devices, the RF system, and also the applications of the combination of these different elements is something I'm working on. So if you have any question or if you want to have a talk, please feel free to contact me on my KU Leuven address or my TU Delft address. I'm available for a talk and collaboration. That would be really nice. So thank you all for your attention, and I hope to talk to you soon.